We have studied about the focal length of convex lens as well as concave lens. Focal length is the distance between the optical center and the focus. This distance is called focal length. Now, if we take two lenses, now the focal length is this only, we can call it f1, f2. So f1 is more than f2. Now if I ask you which lens is more powerful, this one or this one, then the answer should be this one, because it is bending the rays more. The rays were coming in this direction. This lens has been able to bend the rays by this much angle, while this one, this is bending them more. That's why they are converging at a point nearer to the lens. So this lens is more powerful than this one. So power of a lens is defined as the ability of a lens to converge or diverge the rays. And mathematically, power is taken as 1 by f. So reciprocal of focal length is called power. Power for convex will be taken as positive. Power for concave will be negative. For convex it will be positive. 1 by f, unit will be 1 by meter, and 1 by meter we call it diopter. We usually denote it with D. Power of a lens is 2D plus 2D minus 1.5D. It means 2 diopter minus 1.5 diopter. It means concave lens of power 1.5 diopter. Convex lens of power 2 diopter. And this is diopter only when focal length is taken in meter, not in centimeters. Okay. So this is how we define power of a lens. Now what happens if we keep, for a single lens we have done the focal length, we have done the power. What if I keep two lenses in contact? This combination will obviously be more powerful. First lens will converge the rays and the second lens will converge them further. So if the focal length is f1, if its focal length is f2, I want to find out what will be the focal length of a lens which can replace these two and will form the image at the same point where the image is formed by this combination. We call it equivalent lens, or focal length will be called the equivalent focal length. So if I am taking again a point object, lenses are again thin, we are dealing with paraxial rays. This is throughout optics. We are dealing with paraxial rays and lenses, thin lenses. So we will ignore this distance. This one. We will take the distance from the center or from the surface. It will be taken as same. So first lens, it will converge the rays and going somewhere at I dash, but the second lens will further converge it and the image is formed at I. Now just as we have done in case of single lens, lens maker's formula. What was the approach? The image formed by the first surface was taken as object for the second surface and then we took final image. Same here too. I dash is the image formed by the first lens. For the second lens, this is the object and this is the image. Okay, and then we will find out what is the focal length of this combination. So for the first lens, and again let this distance be u. I will take it from the center of the combination. And this distance is v dash and this distance is v. Okay, so now for the first lens using 1 by f is 1 by u, 1 by v minus 1 by v. For the first lens it will be 1 by f1 is 1 by v dash minus 1 by u. For the second lens it will be 1 by, what is v? V is finally v actually, and u is v dash. We have used this separately for both the lenses. Now add them. What will we get? 1 by f1 plus 1 by f2. It is equal to, these two terms will cancel out, 1 by v minus 1 by u. And again, if I take object at infinity, if the rays are coming from infinity, those rays will be converged at the focus. So if u is infinite, we will be f. Take u as infinity, we will be f, and this is the focal length of the combination. 1 by f is 1 by f1 plus 1 by f2. 1 by f is power, that is p1 plus p2. So the power of the lenses, they are added. So if we are using two lenses of power 2 diopter and minus 1.5 diopter, this is P1, this is P2, the combination will have a power 0.5 diopter positive. It will simply be added. For focal length, we have to add the reciprocals to find out the focal length of the combination. So this is all about lenses.